Today, we will be talking about statistical tests that are designed to answer whether you should accept your experimental hypothesis. So there is a huge amount of information available about inferential statistics. I'm just going to go over some of the key concepts and some of the most important ones that hopefully we will be using in our field studies. I'm just going to go through the theory, but if you check the Mathematics for Biologists sheet that I have made available, there is more information. So our learning outcomes for this lecture. First, we should know the difference between type 1 and type 2 errors. We should know the difference between parametric and non-parametric tests. We should understand when you need to transform data and have a basic understanding of some inferential statistics. When we have done our experiment, carefully designed and replicated it, and collected our data, we have done our best to make sure that our results did not occur by chance. We've controlled for as many variables as possible. The statistical test that we use will calculate a p-value. This is a probability value. And the p-value will help determine the significance of your results in relation to the null hypothesis. The null hypothesis states that there is no relationship between your independent and dependent variable. Everything you see is due to chance. The alternate hypothesis states that there is an effect of the independent variable on the dependent. The graph here shows the probability distribution of your data set. On the x-axis is the range of all possible results that could be generated of your dependent variable. On the y-axis is the probability of observations. We can see that the highest point of the bell curve is the most likely outcome for our experiment. It has the highest probability. If we are in one of these small tails on the left or the right, these are much more unlikely observations, and therefore they have probably occurred due to our experimental treatment rather than chance. Statisticians have chosen 95% as the statistical significance threshold. If you get a value of 0.05 or less in your statistical test for your p-value, you can be 95% certain that your result did not happen due to chance. If your variable is less than 0.05, which is 1 in 20 chance, this is the very extreme end of your set of possible results, as we see in this figure. And if you get this value, you will reject the null hypothesis. Your results are statistically significant. If you get a p-value of 0.01 or less, you can be 99% sure your result is not due to chance. So there is a big difference between your treatment and your control. We call this highly statistically significant. We've done our test and we have a significant result. Our p-value is less than 0.05. Our treatment has worked, and we can say that our independent variable causes a change in the dependent variable. But wait, we can never have 100% certainty. A p-value is based on probability, and so we could make a mistake. If we make a decision based on our statistical results, there are 4 possible outcomes that we see in this figure. 2 of these outcomes are correct when we accept the null hypothesis and it is true. Also, if we reject the null hypothesis and it is false. The other 2 outcomes are wrong, and they are named a type 1 or a type 2 error. A type 1 error is known as a false positive. You report your findings as true, but they are actually false. So the null hypothesis is true. Nothing has happened in your experiment, but you report an effect. You can reduce your chance of committing a type 1 error by reducing your acceptable level of P. So instead of looking for P is less than 0.05, a 95% chance, you look for P is less than 0.01, a 1%, or 99% chance. An example could be if you find a positive pregnancy test, but the woman is not pregnant. A type 2 error is known as a false negative. You accept the null hypothesis and say that nothing has happened in your experiment when there is in fact an effect. An example would be if you tested somebody for a disease and decided they did not suffer from it based on your statistical results, when actually they did have the disease. The consequence of a type 1 error mean that unnecessary actions might be taken, while type 2 results in no action being taken when it is needed. Type 1 is generally considered more serious than type 2. We can make a decision on which statistical test to use based on our data structure. If you have interval or ratio data, you can use this flowchart to choose the appropriate test. So all your data is in the form of numbers. This could be counts, measurements, proportions, or lots of other forms. I must also make clear that the data I will be talking about when you're making this choice will be independent, not paired. By that, I mean that you're sampling from different populations. Remember when I told you about the Wessex Bess experiment, and I put a rain shelter in one plot and had a roofed control and an unroofed control in the same plot? These would have been paired. They would be non-independent because they were all in the same plot. So, whereas if you compare 2 different plots, these are independent. Your measures must not be influenced by other samples as far as possible. If you have one experimental treatment to compare with an unmanipulated control, you would conduct a t-test. Your experimental treatment would only have one level, so it would be something like one level of drought against a control. If you had 2 levels of drought and your control, you would require a one-way analysis of variance, or ANOVA for short. We can also have situations where we want to look at 2 continuous variables that change together. For example, we might want to see if body length and weight of a snub-nosed monkey population are related. If they do not directly impact each other, but we think they might be related, we would choose Pearson's correlation tests. If one does impact the other, we would use linear regression. I'll go into these in a little more detail in this lecture. So the tests I just introduced you to are called parametric tests. A parameter is a property of the data, like its mean and standard deviation. Now, if our data set displays central tendency, like in this graph on the left, With the mean near the center of the data set and the data spread evenly around it, we can use a parametric test. We can trust that the parameters are good indicators of the properties of the data. If this is not the case, and the data has a lot of skew, like we see in this graph on the right, we can see it's skewed to the left, so we would have lots of zeros or very low numbers. We need to try a different approach. Before we move to non-parametric tests, we could try a data transformation, which is where we take the natural log or square root or square of each data point. The data in the graph on the right might benefit from such a transformation. If we try that and we don't get a convincing bell curve, we will have to analyze our data using non-parametric tests. These are less powerful and so less desirable than parametric tests because they are based on the median and not the mean of the data. The first test I will talk about is the chi-squared test. This is a good way of analyzing frequencies of count data, such as how many black beetles we have found compared with white. We are essentially asking if the frequency we observe are different to those we would expect by chance. We generate a test statistic from our data based on how many degrees of freedom we have. We compare our test statistic to a table, and it will tell us if our results are significant at a p is less than 0.05 or p is less than 0.01 level. As before, we carry out the calculation shown and sum this calculation for all of our data points. So the observed frequency is what we see in this table below. This is our data. So we've had 10 individuals that fell into category 0, 7 individuals that fell into category 1, 10 individuals that fell into category 2, and so on. So we have 10 categories, we have 100 data points. But you may be wondering how we calculate the expected frequency. The frequency I have displayed here is the observed, which are our collected data. We need to know the expected frequency. I've created a data set of 100 random numbers. If we have the observed frequency, but if they were drawn randomly, we would expect each integer to occur a certain number of times. The expected frequency is the probability of occurrence multiplied by the sample size. The probability of a sample from a data set being in one of 10 categories is 10%. Our data set is n equals 100. 10% is otherwise represented as 0.1. So 0.1 multiplied by 100 is 10. We put it into the equation as below. I've only presented the first 3 values. So you see we have 10 minus 10 squared over 10 equals 0. We have 7 minus 10 squared is 3 over 10 is 0.9, and so on. You can see from my working that our chi-squared test statistic is 5.2. Our degrees of freedom is the number of categories minus 1. We have 10 categories, so we have 9 degrees of freedom. We check the table. We have degrees of freedom down the left side, under the column name R. And for our experiment, we have 9 degrees of freedom. We look at the heading, and in the column marked 0.950, which is chi-squared at the 0.05 level, we see 16.92. Our data are no different to if they had been allocated by chance. In order to get statistical significance, our test statistic would need to be higher than 16.92, but we are much lower, so it is not significant. We have seen no effect of the categories on our data. We accept the null hypothesis, and so our treatments have not affected the respondents. Now we'll talk about the student's t-test. Don't be fooled by the name. The t-test was invented by a man named Student, so it's not designed for students. It is designed to compare the means of 2 continuous data sets. The sample size n for this test would be less than 30, so that's what we mean by small samples. The equation here looks a bit scary, but it isn't really. It's all things that we've come across before. If we look at the equation, everywhere you see a number in subscript that's hanging below the line, that just refers to which data set it's talking about. So remember, we have two data sets we're comparing, 2 samples, and so we have sample 1 and sample 2, and that's all that means. On the top, we have the mean of dataset 1 minus the mean of dataset 2. We do everything in the brackets first, then solve the square root, and then the final division. Let's look at an example. Our example here is male and female warblers, and we are asking if they have different average weights. I have provided some data parameters. As you can see, we managed to catch more females than males. So we have 6 males and 8 females, that's n. We have the 2 means, which is x bar. So we have x bar 1 is 74.8, and the mean, or x bar, of the females is 72.99. We have the standard deviation for both, which is s, and then we have s squared, which is the variance. And we're going to do our calculation. So we'll put the numbers into the equation. Now you might want to pause the video here and just take a good look at how the algebra maps to the parameter values. So where I've inserted the numbers. So first, we solve everything inside the brackets. And remember, if you have brackets and then a number, you see this, so 6 minus 1 in brackets and then 1.08, you would do 5 multiplied by 1.08. You see. So feel free to get a calculator and follow along with this just to make sure that you're happy with how this works. So solving for our equation, we can see that our final test statistic t is 2.55. As for the chi-squared, we check the table of values to see if it is significant. Bear in mind, every statistical test will have a different statistical table So the t-test has its own table for checking these values. Our degrees of freedom are 12. You add the n values together. So that's 6 plus 8. And then you would subtract 1 degree of freedom for the male and 1 for the female. So 14 minus 2 is 12. The tabulated value when we look is 2.179 and our value is 2.55. So we accept the alternate hypothesis. The bird weights are different between female and male. We move on to one-way ANOVA, or analysis of variance. In principle, it is similar to the t-test, but we have 3 or more groups. We could be comparing the weights of 3 different bird species, for example. Assumptions of one-way ANOVA are strict. You must have normally distributed data, with 68% falling within 1 standard deviation of the mean. If not, you could either transform the data or try a non-parametric alternative like Kruskal-Wallis. So you would start by putting your data into your histogram to check for the bell-shaped curve. So with one-way analysis of variance, you will get an F statistic. This will be compared to the value in the table, and you work out degrees of freedom in the same way as the t-test. The ANOVA is based on the variances of the 3 data sets or more, however many data sets you have. It's comparing variances, and it's based on sum of squares. Now, we looked at sum of squares briefly in the previous lecture, and it is the squared value of the difference of the data point from the mean. So you add these together, you square it, and that's what you get. So that's what ANOVA is looking at, whether the means and the variances of the data are different. Now, the reason we do ANOVA and not lots of t-tests is because in statistics, if you were to carry out many tests to get one answer, you run the risk of type 1 errors, finding a false positive. So let's say you had data set A, data set B, and data set C. You could not run a t-test looking at A and B, then one looking at A and C, and then one looking at B and C. This will lead to inflated chances of finding a false positive, and it's very bad. It's a bad thing to do. ANOVA is therefore used to look at the variance around all 3 means at the same time and to give a trustworthy result. So the graph here is from some work that we did. It shows the output of a 2-way ANOVA. So we've got drought and we've got plant species. This is from the Wessex Bess experiment, and we were looking at how drought affects quality of flowers for pollinators. So it was a really nice piece of work. So the factors are flower species. We have Lathyrus pratensis on the left, Onobricus viciifolia in the middle, and Prunella vulgaris on the right. So these are the 3 plant species. And then at the bottom we have control as C, R as roofed control, and then D for drought. And in this graph, we are looking at whether there is a difference between number of flowers per flowering head. So that's called a raceme. And what we see is, well, first let's look at the N. So we have the N, the number of each sample here. So in the control, we have 48 flowers. In the roofed control, we have 46 flowers. And in the drought, we have 44 samples. So each of these box and whisker plots is a combination of the factor levels. The stars in the middle panel are quite a good way of describing significance. So for this species in the middle, Onobricus ficciophonia, we can see that there is a significant difference, and because there are two stars, it's highly significant at the p is less than 0.01 level. One star would be 0.05. And we can see that there is a significant difference between the control and the drought. There are more flowers in the control than there are in the drought. That means that the loss of water has significant impacts on the ability of the Onobricus to flower, and this might have implications for the availability of nectar for the pollinating species. The other two species do not have any significant stars. For Lathyrus pratensis on the left, this could be, so these are the medians, these lines, this could be because there really isn't an effect. For Prunella vulgaris, there does look like there's quite a big difference in medians, but there's a lot of variance. Look at the size of this whisker. So there's so much variance, so much difference that we simply cannot detect a signal of the drought. It's hidden, the effect of the drought, if it is present. And this is why we really want quite low variance if possible, and why you try to control for as many factors as possible in an experiment, because it could be any number of reasons why we have so much variation in this droughted prunella. So the final thing is you might need to do what is known as a post hoc test. So we would have done a post hoc test here, and it's just to see which treatments are different from the other treatments. So what we seem to have, because the line is looking at this one and this one, it seems that these two are different from one another, but the one in the middle has no difference. It's somewhere in between. So there's no difference between the roof control and either control or drought. It's just the other two treatments are different from one another. Pearson's correlation is looking at whether two variables co-vary, whether they change together. Correlation is a technique that measures the strength of a relationship between two quantitative, continuous variables. The relationship could be positive, where both increase together, or negative, where as one increases, the other decreases. One example could be, does blood pressure change with age? And you might expect to see a positive relationship like we see here on the left. You first have a look at the data to see if it is worth testing by plotting a scatter plot, and all three of these are examples of scatter plot. If you have a perfect fit, as we do here, you see R equals 1. These are perfect fits. There is probably something wrong. If you use statistical software, it will try to plot a line of best fit through your data. This is a line that has the lowest distance from the points possible. Your data will always have variance, which means there will always be a scatter, like we see here. This is very unlikely, and you should suspect that something has gone wrong if you get an R of either 1 or -1. That's just not going to happen with ecology data. In ecology, there is so much variation with everything we measure that an R value of over about 0.3 or 30% fit is seen as good. This graph here is pretty strong. The fit is based on the distance of each point from the line of best fit and then squared. Again, we see the sum of squares, which we've met previously. ANOVA is based on it. It's just a useful measure. Please be aware, though, that just because you see a strong linear relationship does not mean that one caused the other. Also, with Pearson's correlation, because we are not saying that these directly impact these, it doesn't matter which axis you plot your data on. This is the golden rule in statistics. The relationships that you see between variables must be supported by sound theoretical reasons why your variables are linked. Correlation does not mean that one variable causes the patterns in the other. So correlation does not imply causation. Our final statistical test is linear regression. Like correlation, we expect the relationships between our variables to be linear. That is, they fit to a straight line. But in this case, one variable is caused by the other. Here we have independent and dependent variables again. For example, temperature is the independent variable, and plant growth rate is the dependent variable. Again, we plot the data in a scatter graph and make a line of best fit. This line is called a regression line, and it is the result of a mathematical equation that predicts the values of the dependent variable based on the independent variable. Please note that we cannot predict the dependent variable beyond the range of the independent. Something unexpected might happen at higher values. So, for example, if you were to look at enzyme activity and you only looked between 0 and 30 degrees centigrade, you could not predict activity at 50 degrees centigrade because the model would not be able to predict that the enzyme will be killed at 40 degrees. So it would probably just give you a constant increase to 50 degrees, and we know that that can't possibly be true. So you must not try to extrapolate beyond the range of the independent variable. We are looking to predict the value of plant growth rate at a given temperature. We again get a value of the fit, and it is usually presented as R squared. So you see here that the R squared is 0.7952. Now, this is about 80% fit, which is very, very good. R squared is bounded between 0 and 1 and can be considered as a percentage of the fit. Every straight line on a graph has two main parameters, and this is what we're trying to calculate with our linear regression. We are calculating the intercept, which is where the line meets the y-axis, so A on the graph. You see that it cuts just above 0.1. And then the other parameter is B, the slope, which is the steepness or gradient of the line. So I've placed the correct equation on the graph for your reference. And you can see that the intercept is 0.1169. The equation is the other way around here, but it doesn't make any difference. And the slope is 0.6334. If the independent variable increases by 1 point, so if we move from left to right by 1, you see 1, then we should have gone up by 0.6334. And you can see if you were to make a triangle and you measured it, you see that 1 here is just above 0.7. It is, you would subtract this from this and you would get 6.334, or 0.6334, sorry. So linear regression is a very important predictive tool, but you must use it with some caution, and you cannot go beyond the range of this data. So this data goes beyond, goes to 1. We have no way of knowing what happens at 1.2. We can suggest that it might continue up and end up at about 0.85 possibly, but like with the enzymes, we just don't know. There might be a sudden drop in activity, so we cannot make that prediction. So in summary, type 1 errors are false positives. Type 2 errors are false negatives. Parametric tests are based on the mean being the central point of the data set and the data being normally distributed. Parametric tests have more statistical power than non-parametric tests, so we should use those ideally if we can. And the structure of your data set will dictate the appropriate test to use.